Hello students, welcome back to our DBMS course. Now we are moving to the next sections, the part 2 of chapter 3. So we are still discussing about the file organization. So in this chapter we will see another method of how we organize a file. It includes the indexing and then B3 index files, B class 3 index files, and then we will look into a comparison of different file organizations from the last uh, meeting. Yeah, it's still chapter 3, but part 1. And then we will see into some of the factors which affecting choice of file organizations. All right, so we're going to start with indexing. So in this sections, we will understand index as a collection of data entries, which is used to locate a record in a file. Okay, so an index in file organization is like a shortcut to help you to find information quickly without going through everything one by one. So here's the simple one. So indexing field, this is like a label or identifier which is created from some part of the information you are storing, like a person's name or ID number, and it will help you to find what you're looking for faster. And the second component is a pointer. So this is a link that tells you exactly where the information is stored in the memory. It's like a pointer or an arrow showing locations. So think of it like the index at the back of the book. So the index in the book lists important topics like a person's name or a subject. Next to each topic, it will give you a page number, which is in this case a pointer, that tells you where to go in the book to find more details. So instead of just flipping through every page in the book to find something, you will just need to check the index and find the page numbers and then go directly there. We're talking in a computer system. Instead of searching through the whole memory, which is will take a lot of time, the system looks at the index first to find the locations of the data. And after that, it will go directly to that spot in the memory to get the record. So the index will make searching faster and more efficient, just like using a book's index to find topics quickly. So there are some types of indexing. Yeah, so types of indexing is some ways to organize data so that you can search for records quickly. So there are two common types. The first one is ordered indexing. So in this method, the records in the file are stored in a specific sorted order, like alphabetically or numerically. The index values, which helps point to these records, are also stored in a sorted manner. This makes it easier to search for records using techniques like binary search, which is very fast for sorted data. Let's think of a library where all the books are neatly arranged in alphabetically order by title. If you want to find a book, you don't need to check every shelf. Since the books are sorted, you can quickly narrow down your search by checking sections, just like how you would divide and conquer when searching in a dictionary. So maybe the title of the books is starting from a letter A, then you can just directly go into self with letter A, something like that. So ordered indexing is useful when you need to search efficiently through shorter data. And then the next type of indexing is called hash indexing. So in this method, the records don't need to be sorted. Instead of hash function is used to place records in the hash table. So the hash function takes the key like a student ID and then transform it into a number that tells you exactly where the record is located. So we don't need to search through sorted records. The hash functions will give you the direct access, okay, the direct access to the data. Imagine a large parking lot where cars are parked randomly. Instead of wandering around to find a specific car, you can use just a special device, which is, we call it in this case, a hash function that instantly tells you exactly where the car is parked. The hash indexing is best when you need a quick and direct access to records and when the records are distributed evenly across the storage. So in summary, the ordered indexing is more like records and index values are sorted, making searching faster, especially with techniques like a binary search. When talking about the hash indexing, the records are spread out using hash functions, allowing for direct and fast access without needing to shorten them. So both of these methods will improve your search efficiently, but both are suited for different types of data organizations. So for ordered indexing, it has four types. Okay, we will discuss one by one. So as you can see in the figure, there are two types of indexes in this case. We have dense index, which is on the left side, and also sparse index. Okay, so what is dense index and how it works? Okay, there's an index entry for every unique value of the search key attribute, and each entry points to the first records with that value, and subsequent records are stored sequentially. Okay, I believe that you are quite confused with these descriptions, so we'll just jump into an examples. So if you check the middle table, it's over here. Okay, we have name, we have age, and we have a salary over here. Okay, and if you check closely, there are names that appear twice, right? For example, we take Amit. So Amit appears twice in the table. So the dense index has an entry for Amit. Okay, which is actually points to both records over here. And there's an entry for each of uh, search key value, which is makes searching very quick and efficient for smaller data sets. And the disadvantage is that the index can become very large because of many entries. Okay, that was the dense indexing. Now let's move on to the second one, which is called sparse index, which is on the right side of the table. So instead of having an entry for every search key value, the sparse index only includes an entry for some values. Okay, so it's only for some values. The sparse index points to a block of records where you would then search for a specific value. Okay, jump into examples. So the sparse index for this table will include only two names, right? Okay, we move to this index, which is called sparse index. So we have two names, Amit and Sonal. It's not all names, only two names over here, right? So for sparse index, it uses less memory because there are fewer index entries. And it's more efficient for larger files. But searching can take longer since you may need to look within the blocks of the records. Okay. So in summary, I can sum up that the dense index, which includes every search key value, is indexed. We can make it easier to find specific records, but requiring more memory because we have all the records over here. But for sparse index, there will be only some search key values, yeah, which is indexed, and it will save memory, but it will might require a bit more searching within a blocks. So it's amide over here, and then we have these blocks. So this is includes the amide index, which meanwhile for sonal, it's for this. Okay, or maybe I use another colors. Okay, okay. So for amide name, it includes this block. Okay. Meanwhile, for sonal, which includes this block. Okay, this is a sparse index. Okay, this is sparse index. Okay, moving to the next type of ordered indexing. It's called cluster and non-clustered index. So cluster index, where the records are stored physically in order according to a non-prime key attribute, clustering fields. and it's similar to dense indexing, and a file can have only one cluster index. So in simple way I can explain is in cluster index, the data records are stored physically in the order of the index. The actual data is sorted based on the index key. There is only one cluster index per table because once data is physically sorted in a particular order, it cannot be reordered for another index. So the index directly points to the data records. So when you search using the index, the system quickly finds the records because the data entries are stored in sequence. So let me give you examples for a better understanding. Imagine you have a phone book, okay, that is already sorted alphabetically by last name, and the names in the index are in the same order as the entries in the books. So you don't need to jump around, just follow the order. So useful for range queries, which is to finding all the records between two values because the data is stored in order, which making it easier to find the records. So if you want to check is the cluster index is like this. Okay, so as you can see here, the arrow is very neat. Okay, so the next is called non-clustered index, which is on the right side. Okay, which is in the right side. So non-clustered index is an index that does not affect the physical order of the records. So a file can have a multiple non-clustered index. So in a simpler way, I can explain. In a non-clustered index, the order of the data does not change. The index is separate from the actual data, so the records can be stored anywhere in the file. The non-clustered index contains pointer that point to a data records. It's like a map that helps you to find where the data is stored. But the data itself is not in a particular order. So it's, I can say it's randomly stored, something like that. So a table can have a multiple non-clustered index as do not interfere with the physical arrangement of the data. Okay, let me give you an example. Imagine you have a book with an index at the end of the book, which is listing the topics and their page numbers. The book itself is not arranged by the index. The topics could be anywhere, but the index helps you to find them by pointing to the correct pages. Okay, so that is the difference. The non-clustered index is very useful when you have multiple fields that you want to search by, as non-clustered index are flexible and can be used on different columns. So in summary, the cluster is when the data records are stored in the same physical order as the index. So it's same with physical order, okay, with the real file. So there can only be one cluster index per table because the data can only be ordered one way. Meanwhile, for the, let me choose another colors. Meanwhile, for the non-clustered index, the data is not stored in order of the index. Instead, pointers are used to locate the data. So there's a pointer. The multiple non-clustered index can exist for a table in this case. So the visual highlights how the clustered index directly affects the physical layout of the data, while the non-clustered index are like separate maps that helps to find the data without changing its storage order. The next type of the ordered indexing is called primary and secondary index. So primary and secondary index are two methods used to speed up search in a database. So we will call each of these. The first one is called primary index. Oops, primary index. So the primary index is built on the prime key attribute like the unique identifier or primary key of a table. This index will help you to find records quickly by using techniques like binary search. So the primary index is usually sparse, meaning not every record has an index entry. Instead, it indexes key points and the system searches through these to quickly find the range where the actual records lies. There are some advantages of this primary index. First is fast search. So searching is quick because the index allows direct access to the records using the binary search. And also smaller index. Since it's sparse, the primary index takes up less memory. And also uniqueness. The primary key ensures that each value is unique, making the index highly reliable. So in the table, for the primary key is using the ID, okay? Let's think of the same, yeah, we're still using the same table like previous. Um, let's think of a school yearbook, okay? Okay, I will leave the table here. I will explain to you another example of this case. Okay, so think of a school year book where students are listed alphabetically by last name. So the primary index would have you to quickly find a student's page by narrowing down the sections, but it's based on a unique value like student ID. Okay. So moving on to the next type is the secondary index. So it provides a secondary means of accessing a data file using a non-prime key attribute. It is always dense and allows fast searching based on non-prime attribute. The secondary index is based on non-prime key attributes, meaning that attributes that are not the main key, yeah, for example, like student age or city or last name, and this index provides a second way to search for a data. So unlike the primary index, the secondary index is always dense, meaning that there is an index entry for every records in the file. Okay, so if you check the table, okay, I will use a table in this case. So the primary index is using a search key of ID, employee ID in this case, in this table. Uh, so that's why we call it uh, a primary. Okay, so that's why it's called a primary key. And then for the secondary key, in this table, we are using an H, yeah, as the search key. So we have 20, we have 21, 24, 30, and 40. So this is the secondary index. Okay. Okay, let's move on to the next type of this ordered indexing type. It's called single and multi-level indexes. So a single level index is a straightforward and involves just one stage of indexing. In this approach, there is one index table that points directly to the data records. It's efficient for small to medium-sized files as the amount of data being searched is limited. There's a limitations of using this kind of index. As the file grows in size, the index also grows, making searching slower and less efficient. Okay, imagine that we have a list of 100 names, and then we will create an index for the first letter of each name. When we search for a name starting with S, we can directly go to the sections where S is fine. Yeah, for example, we have A, B, C, okay? So we directly go to the sections where S names are stored. So this is how we use the single level index. Meanwhile, for the multi-level index, it's for the larger size, larger files. A multiple index is used to reduce search time by dividing the index into multiple levels, okay? Because this is multiple, so there are some steps or there are some layers or levels, yeah, of the index. And each level directs to search to the next level, significantly improving search efficiency for large data files. Okay, so the index is divided into multiple levels. So it's like a hierarchy. And the first level points to the seconds, and the second level points to the data record, something like that. And these structures reduce the search time as fewer steps are needed to locate the desired records. And again, it's for a large databases. So in the picture over here, we have uh, the examples of multi-level indexing. So the image illustrates the concept of multi-level index, which is a method used in the database system to improve a search efficiency by reducing the number of disk access needed to find a data records. So because it's multi-level, so we have some levels, right? Okay, so let me just do okay. Okay, so this is a multi-level index, okay? So this is called a first level index. This is the top level of indexing, and it contains a list of block value pointers that corresponds to ranges of values. Okay? Uh, After we reach the entry, okay, so each entry in this index points to a block in the second level of index. So after you go through the first level of index, and then we move to the next level. In this case here, this is the second level of index. And in this level, we have each block at this level is pointed to an entry by the first level index. And these blocks contains pointers to the actual data. Yeah. So for examples, we have here, and then we will go directly to the records. The second level index further narrows down to the search range specified by the first level index. And then the data file. And then we reach to the data file. It is where the actual records are stored, and each record has files such ID, name. Oh, sorry, I shouldn't go here. Okay. ID, name, then age and salary. Okay. So again, how a multi-level indexing work. So there is a first level index when a search. I need to sorry, I need to go back and forth. Okay. So we have first level here. When a search query is issued, the system will first looks at the first level index to determine which blocks in the second uh, level, which is contains the data, and then and then the next block, which is contains the data. For example, if we are looking for a record with a specific ID, the system will determine which range of IDs, yeah, in the first level index points to. Okay, so moving on to the next one. Yeah. the second level index. Okay, so once the correct block in the second level index is identified, the search is further refined. The systems will look within this block to find the exact pointers that leads to the data files. And finally, the data files. The pointer from the second level index points directly to the records of data files here. And then the systems will retrieve the records. Yeah, for examples. In this case, we have an ID, we have name, and age, and salary. Oh, sorry. Okay, let's move on to the next sections. We're talking about B3 index file. So there are actually B3 and B plus 3. Okay, let's just check. So what is a B3 index? So a B3 is a structure used to organize and manage data efficiently within a database. And it allows for fast searching by creating a hierarchical index that can quickly narrow down the location of data records. The B trees are designed to keep the tree structure balanced, meaning that all paths from the root to the leaf nodes are the equal length. And this balance is crucial for ensuring that search operations remain efficient, as it minimizes the number of comparisons needed to find a records. It is also to prevent wasted space. So B3 will ensure that nodes are at least half full. It means that they are filled to a minimum capacity. This will prevent wasted space within the index, making it the most efficient use of storage while still allowing for room for future growth as the records are added or removed. So there are some properties of B3 under of order M. So each node in the B3, except for the root and the leaf nodes, must have between M2 is a floor of M divided by 2 and M sub trees. Okay. This will ensure that the tree remains balanced as each node has a minimum number of children while also allowing for a maximum number of children. The root node must have at least two subtrees unless it is a leaf node. And this property prevents the root from being a dead end and ensures that there is always a branching structure in the tree. And all leaf nodes in the B tree are located in the same level, which means that they have to keep the same distance from the root. This uniformity ensures that the tree is balanced, providing the efficient search time across the all records, as each path from the root to any leaf nodes takes the same number of the steps. So we have two types of the structure. And the first one is node types. The node types has two types. The first one is non-leaf node, and the second is leaf node. So the non-leaf node is a pointers. Yeah, it has two types of pointers. The first one is the PI, is the pointers to another node, and it connects to a child node in a B tree. It helps to navigate down the tree to find specific records. And then we also have RI, is the pointer to record block. It connects to a record block which stores the actual data associated with a key. So we have also key I, which represents the key value. Each non-leaf node contains a key value that acts as a reference point to determine which child node to follow during a search. And this key value will help to maintain the order within the tree. Moving on to next one is leaf node. So leaf node only have one pointer, yeah. It's the PI, yeah, which is connects directly to the record blocks where the actual data stored. And in leaf nodes, there are no child nodes to navigate to, as they represent the end points of the tree. Okay, and it's the same with the non-leaf node. We also have the leaf node also have a key value, which is represented by Ki, and it helps to identify the data stored in that node. So the key values in leaf nodes are used for searching and organizing their records. So in summary, the difference between a non-leaf nodes and leaf nodes is the multiple pointer and single pointer. Okay, so for the non-leaf nodes, it helps in navigating the tree structure with multiple pointers to child nodes and record blocks, which is ensuring that searching remains efficient. Meanwhile, for the leaf nodes, it serves as the final destinations for the data retrieval. It contains the pointer to actual data records. Okay, and the key values is needed for the index. Okay, so the non-leaf nodes is for multiple pointers, which is pointers to child nodes. Meanwhile, for the leaf nodes is a pointer to actual data records. Okay, that's the difference. Moving to the next one, this is the diagrams in terms of B tree for file employee. This represents the B tree structure used to index the employee records. So we have a root node here, which contains the pointers to child nodes and key values. the key values of employee names. And in this diagram, the root node has two keys. This is called root nodes. Okay. And each key, yeah, points to either a data bucket, like which is a collection of records, or another node in the tree. Okay. And then we have a child nodes. This child is below the root, which is contains the further keys and pointers. And in this diagram, the node under the go route has two keys. Okay. Oh, sorry. So the node under go route is has two keys. In this case, we have Amar and we have Sirac. And then change the colors. And then the nodes under Naveen has three keys. It's Harish, and then Lalit and Praveen. Yeah. And then the leaf nodes. The leaf nodes are at the bottom level and contains the actual pointer to the data buckets, or we can say an employee records. For instance, the Amar key. Let me choose another colors. Okay, the Amar key and the leaf node points to the Amar bucket. Yeah, Amar bucket. Sorry. The Amar bucket, it holds the records for the employee named Amar. Okay, so how it works? To find an employee's records, the search start from the root nodes. Yeah, start from the root nodes, which is over here. Okay, for examples, I want to find Lalit. Okay, I want to find Lalit, and the search begin at the root. Yeah, over here, then the root nodes, and follows the pointer. Yeah, it follows the pointer from Naveen to the nodes containing, Haris and Lalit first. Okay, once the once at the correct node, the search will identify the key of Lalit and follows the pointers to the Lalit bucket. When adding a new employee, the correct positions in the tree is found based on the name. So if the node where the new key should be added is full, the nodes will be split and a new key is inserted. And this might propagate upward. Splitting parent nodes is necessary. Okay. Now, when it comes to deletion, yeah, deleting an employee records involves finding the correct leaf nodes and removing the key. If the deletions causes a node to have two view keys, it may need to borrow keys from siblings or merge with a sibling node, which can propagate change up the tree. Okay, so this is root node. Okay, contains Gaurav and Naveen. Gaurav points to node containing Amar and Sirak. Okay, and meanwhile for Naveen, points to nodes containing Haris and Lalit and containing Praveen. So this is the first child of the nodes, which is under the Gaurav, which is Amar and Sirak, and then Amar points to the Amar packet, and so on. So the key operations in B3, I have little explanations before in the previous diagram. So let me just uh, tell you once again. So the searching, the search process begins at the root or top of the tree, and then it moves down through the tree and then comparing keys at each node to find the correct path. The search will continue until it reaches the leaf nodes or to find the desired records. Yeah, and then when it comes to the insertion, which is to find the spot, or first we need to find the spot, and then to insert a new records, the tree first needs to find appropriate leaf nodes where the new record should go. Then the nodes will split, and then the new records will be inserted or will be added. And the next is deletion. So it's a removing records. It's kind of tricky actually, especially if the records is not in a leaf node. And if a record is removed from a leaf node and then the node becomes too empty, it might need to merge with a neighboring node. Yeah, it's quite complex process for the deletion because it might affect the other nodes and potentially the structure of the tree, of course, and making it more complicated than insertion. Okay, so this is the advantages and disadvantages of B3. Uh, we move. Okay, so we're talking about the advantages first. So, the advantages of using the B3 index files is, of course, reduce the redundancy. Um, because it use in a B tree, the each key values appears only once within the tree. This means there is no duplication of keys, which conserves memory and reduces the complexity of managing multiple copies of the same key. And it's faster, right? It's efficient. And B3 allows for quick search because they use a balanced structure, and its comparison in a B3 reduces the search space significantly, making it much faster than scanning through an entire index sequential file. And efficiency with the large files. As the database grows in size, B trees continue to perform efficiently, and the tree structure will ensure the height of the tree grows systematically with the number of the records, and keeping operations like search, insert, and deletion efficient even with the large data sets. And then when we are talking about the disadvantages, so we have some drawbacks to consider, right? It's a complex records updates, yeah. When updating records in a big tree, changes might need to propagate through various levels of the tree. For example, if you insert or delete a record, it might necessitate rebalancing the tree, which can be a complex process. It is also less efficient compared with the B plus trees, which will be discussed later. The B trees um, can be less efficient than the B plus trees, especially for range queries. The B plus trees are specifically designed to handle sequential access more efficiently because all the data pointers are stored in the leaf nodes which are linked together. So in contrast, B trees stores data pointers in all nodes, which can make sequential access slower. And direct files. So direct files which use the hash tables for indexing can be more efficient for certain types of search because they provide constant time complexity for lookups. However, they lacked of flexibility and ordered structure of B trees. Talking about the search time in a B tree is proportional to the logarithm of the number of search keys. While this is efficient, meaning it grows slowly as the number of keys increases, so it still indicates that the search time increases with the number of keys. This is less of a drawback in the practice, but is worth considering when compared to direct access methods like hash tables, which offer constant time lookups. Okay, so we are moving to the next one, which is called B plus tree index files. Okay, so what is B plus tree? So a B plus tree is a type of balanced tree commonly used in a database for indexing. This balance ensures that operations such as search, insertions, and deletions are efficient. So unlike the previous one, P3, P minus 3, okay? So in a B plus tree, all paths from the root nodes to the leaf nodes have the same length. This uniformity helps to maintain the tree's balance and ensuring the consistent performance. And the structure of a B3 supports both direct access, finding a specific items quickly, and sequential access, which is traversing items in a sorted order efficiently. This dual capability makes the B plus tree versatile for various database operations. So the B tree structure, yeah, it's in a B plus tree. Each node in a B plus tree can have a number of children. Yes, we're talking about subnodes. Yeah, we can also call it by subnodes. And that range from n divided by 2 to n children, okay? I think I need to change the colors. Okay, so each node has between n per 2 and n children. So these rules will ensure the tree is balanced, meaning that all leaf nodes are at the same level and helps balanced helps to maintain the efficient search times. Okay. And the leaf nodes are the end nodes of the tree, and they store the actual data records or pointers to the data buckets. A bucket is a collection of the records. Since the leaf nodes directly points to a data, retrieving information is quick and efficient. And next one, the key. Yeah, the key or search values within its nodes are kept in the sorted orders. And this sorting is crucial for the efficiency of the B plus tree. It's fast, yeah. The sorted order of key allows the tree to use binary search within nodes, speeding up the process of finding the specific keys or data. Okay, let's have an examples for your better understanding. So imagine a B plus tree where each node can have a maximum uh, of 4 children, yeah. So okay, I will draw here. So and equals to 4, okay. And so every node except the root and leaves will have at least 2 and at most 4 children, okay. So maybe I will draw over here. Okay, okay. This balance will ensure that no part of the tree is too deep, maintaining the quick search time. So suppose we are storing student records in a database. The leaf nodes might directly contains the student's records, yeah. So here is the student's records, okay, or pointers to where these records are stored. And then talking about the key values, within each node, the student IDs are kept in ascending order. If a node has keys 102, and then 205, and 307, 409. They are sorted in that order, okay? And this sorting means that if you are looking for a student ID of 205, you can quickly determine it's between 102 and 307, which is narrowing down your search efficiently. So by maintaining these key properties of B plus tree, it provides a robust structure for efficient data storage and retrieval. So there are some operations in B plus tree. It's almost the same. Yeah. We have a searching, we have insertion, we have deletion. Okay. So the searching will begins at the root nodes and may finish before reaching the leaf nodes. Yeah. So it uses the shorted structure to quickly locate the desired key. And the next one is insertion. So the first locate the appropriate leaf nodes where the new record should be placed, and then add the new records to this leaf to or create a new bucket if necessary. They may be a node split, yeah. If the leaf node is full after insertion, it may split into two nodes to accommodate the new record. The last one is deletion. So remove the file from the leaf nodes. If the record was in a bucket, the bucket might become empty. And if removing the record leaves the node under full, it may merge with a neighboring node. Now this merging can continue up to the tree, even reaching the node, even reaching the root. So always there is there are advantages and disadvantages of using something. So we need to know why we use B plus tree index files. The B tree allows you to quickly find specific items without scanning through everything, right? And then it's also great for sequential and arranged queries. They work well for finding items in a specific order or within a certain range, and also fast in searching. Since the keys are shorted, it's quicker to look up information. However, they have some drawbacks of B plus tree, sorry. Uh, the complex of insertion and deletion. So adding or removing items in B plus tree is more complicated compared to the B tree. And because the search key values are repeated, the B plus trees use more memory in this case. So let's compare B tree versus B plus tree. So B plus tree have separate leaf nodes storing data or pointers. Meanwhile, in in B, sorry, let me say it again. So in B plus trees, all actual data is stored in the leaf nodes, while the internal nodes only store keys and pointers to help with the navigations. This will keeps the tree balance, yeah, and optimize the searches. The B plus trees also provide faster range queries due to the structure of leaf nodes. Since the leaf nodes are linked sequentially, B plus tree allow for efficient range searches where you can quickly find all records in a specific range. The B trees store data within the internal nodes. Now the B tree store both key and data in internal nodes, which can make the tree smaller. However, this leads to more complicated search and update operations because data may be scattered throughout the three. To sum up, the B plus tree provides balance, efficient indexing for direct and sequential access, Meanwhile, the complexity of insertions and deletions is trade-off for faster searching, and it's ideal for databases with large datasets requiring the rich queries. So let's compare some different file organizations. So this table will outline the differences between the three common file organizations technique. It's the oops, sequential, and then index, and the hash or direct. Okay, I think you can just read by yourself, yeah? The comparison between these three file organizations method. Okay, let me just read for you two numbers over here. Okay, so in sequential, there is a random retrieval on primary key. On a sequential, it's hard to quickly find a specific records using its primary key. Meanwhile, for index, you can find a record faster than sequential, but it's not the fastest. And for hash direct, you can find a record instantly by its primary key. In terms of wasted space, the sequential, there is no space wasted, and all data is stored in order. And for index, no data space is wasted, but you need extra space for storing the index. Meanwhile, for the hash or direct, the extra space is required to allow for easy addition and deletion of records. And the rest you can read by yourself, okay? So there are some major factors that affect the choice of a file organizations. So the choice of file organizations depends on several key factors, each of which affect how efficiently records can be accessed and managed in a database. So the first is the access type. What it means. Uh, do you need to access records in a specific order, the sequential access, or can you randomly pick a records in a random access? For example, if you want to access all records in order, sequential is better. If you need to jump to specific records frequently, random access methods like hashing or indexing are more suitable. And then access time. How long does it take to find our specific records? If speed is important, you might use hashed or indexed files for faster access. Sequential access may take longer as you may have to go through many records to find the one that you need. And the next one is file size. The size of the file impacts which organization method works best. If the file is very large, the direct access method like hashing might be better, as they can quickly locate the record. And for smaller files, the sequential access might work just fine. And then overhead. This refers to the extra resources required by the method, such as the extra space or processing time. The fast methods like indexing might waste space by storing the extra information, like the index itself, while slower method might save space but take more time to access the records. The next factor is about updating time. Okay, so how easy and fast is it to add, to delete, or to modify records? If you need to frequently update the records, for example, some methods like hashing will allow for fast changes, while the others, like sequential files, might require rewriting large portion of the file, which of course takes more time. And then complexity. Some file organizations methods are more complicated and costly to implement. More advanced methods like indexing or hashing can be faster but are also more complex and may require more expertise and money to set up and maintain. And the next one is the availability of the hardware. The type of hardware available might limit your options for file organizations. So some hardware, like tape drives, only support sequential file access, meaning that you cannot use random access methods on such devices. So those factors will help to design the best file organizations method based on specific needs of the system, balancing speed, complexity, and the availability of the resources. Okay, if you have any questions, you can just send me a message. And if you don't have any questions, then you can start to doing the assignments on the iLearning. Okay. I will see you in the next chapter. Goodbye.